Hello everyone, happy holidays and welcome to the OneClass channel. My name is Fejiro and I am an Honors Bachelor of Science student working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some homework or help or tutoring actually, you can actually click on the link in the description below. And with that, thanks to our introductions, we can now officially begin this session, starting with question 1. So, as you can see, the first question asks, if it takes 5 years for Juno to reach Jupiter, what is the average speed in miles per hour over this period? So, question 1. Alright, so 5 years. And they want to know average, oops, that's bad writing, average speed in miles per hour. Let's actually zoom in here so my handwriting can be a little bit more crisp. So that's the whole question there. And if you want to see it here, you can see it on the other screen. So with that, let's begin. So first, let's break down based on the information we had. It took her 5 years and they want to know her speed in miles per hour. So 5 years is the time, okay? And so we need to convert 5 years into hours. So the way that will work is that, well, we definitely need a calculator for this one, but we need to know how many years, how many hours in a year, and then we just multiply that by 5. Make sure you keep your units. So with this, actually, you can just, if you're given a, conversion sheet, that works a lot easier. But this one's a little bit tricky when it comes to time because it's usually easier to search it up. But simply put, how many hours in a year? So this is what they're giving us. There's 8,760 hours per year. And the reason why I wrote it like that is because it's important to keep your units. And you know what? While we're here, they're asking us specifically in this question, Juno to reach Jupiter. We're assuming that they're starting from Earth, okay? And so distance from Earth to Jupiter. So we have 799.04 million kilometers, which is actually perfect because this helps us with our conversions. So we're given now the way to do these questions. You need distance over time. That's how you calculate speed. Okay, so actually I'll write it here. So velocity, well, speed, velocity is a little bit different because it includes direction, but speed is equal to distance over time. Okay, and now that we have that information, we're given the distance and we're given the time, 5 years. Okay, so now we have to work on converting this. I'm going to use a different color so we can keep track. So let's work on distance first. They're asking for average speed in miles, not kilometers. And now here's where, if you do have a conversion sheet, that's great. I actually pulled up some conversion sheets specifically for this because in this lesson there will be quite a few conversions. So here we have it. So for length, 1 mile is 1.609 kilometers. Okay, so with that, okay, so we wanted to go from kilometers to miles. So the way I do it to keep my units, it's actually like this. So I have, let's write down a lot simpler because 799 million, so that's times 10 to the 6. So I really have 799.04 times 10 to the 6, because 10 to the 3 is 1,000 because that's 3 zeros. Okay, 10 to the 6 is 3 more zeros, so that's 1,000,000. That's how we figure that one out. So with that, let us continue. In order to make this a much nicer number, I'm actually going to move some digits around going to move this over here twice, and by doing that, I actually add 2 here. So the actual distance we have right now is 7.9904 times 10 to the 8 kilometers. And now we want to convert it to miles. You always want to put the thing you're trying to convert to in the numerator, so it's 1 mile, and according to this sheet it equals 1.609 kilometers. And the reason why we do that is because we want to make sure that units cancel out, numerator, denominator there. So by dividing that number by 1.609, we will get the amount of miles. So I'm going to quickly put this in my calculator. Okay, .609. So we get around 4.966, well, times 10 to the 8 miles. All right, so we have our first number. Okay, and now we want to get that time. It says miles per hour. So like they discussed earlier, we have 8,760 hours per year. So now you want numerator and denominator the same way. So 5 years, okay, times 8,760 hours in 1 year. Okay, so what does that give us? 5 times 8,760. This is the amount of total hours we have, 43,800. Okay, and that means we have now hours and we have now miles. So now if you want to match the miles per hour, you have to divide the miles by the hours. So now we have 4.966 times 10 to the 8 miles over 43,800 hours. And then you just plug it into the calculator. So all right, so we have 1.1338. I'm just going to round it there, and then we'll discuss significant digits after, but I just want to get a number real quick. Times 10 to the 4 miles per hour. And now back to the original question. So there we go. It says 5.0 years. The reason why now significant digits matter, they only gave us 2 with the 5.0. So here it's really, the answer is just 1.1 times 10 to the 4 miles per hour. That should be the answer. Let's see how they discussed it. They do discuss speed equals distance over time, which is correct. They have that total miles based on, yep, the kilometers. Our kilometers were a little bit different, just let's pull this straight from Google. But as long as our numbers are relatively in range. So I get 1.1 times 10 to the 4, and they got 10,901, which coincidentally is, if you round it, it is 1.1 times 10 to the 4 miles per hour. So this is correct. And with that, we've answered our first question of many in terms of how to work with units. So now the second question. All right. Describe how the volume of a regular solid can be determined. So this question is more of a conceptual question. Now for this one, okay, it's a regular solid. It's not a liquid, but they're asking in terms of volume. So the technique commonly used, as they'll describe most likely in the answer here, is through volume displacement. So usually if you want to find, you know how you can see like, let's say like a rock or something, right? I don't know why I do it like that, but a rock. And then they'll say like this rock is like 34 grams, or like they'll actually put 34 volume sometime. I mean 34 milliliters, something like this. The reason why they can even say that is because most of the times what they use is a technique called volume displacement, and this is key because this only applies to, you know, solids that do not dissolve in that liquid. So what it does is they usually just get a beaker or a glass with indicated markers on it. Alright, they fill it with water, and then they throw the solid in. Okay, and then there's a change. Once that solid goes in, right, there's displacement in the water. This volume displacement, okay, this amount right here is what they use to determine the volume of an irregular solid. So let's say this marker was at let's say 4 mil, and then the volume was placed like 4.5 mil. The volume of this irregular solid would be 0.5 mils. So that is the trick here in regards to this, at least in describing it, because what you have to understand is that the whole concept of, you know, matter can't be created or destroyed. It's just transferred, whether through energy. But point being is, like, because it takes up so much space in terms of the surface area, that space now has to be accounted for by the water level rising, and hence how we get this. Now this does only work specifically, as I said, for solids that do not dissolve, and also solids that are not buoyant. Depending on the buoyancy, it has to be fully submerged. If it's not fully submerged, you can't really say, like for example ice, it's hard to say the volume of that solid because it usually floats on top of the water. But for heavier things that are more dense, like metals, coins, throw a bunch of coins into water. Actually, it's a cool way to find out how many coins you have in regards to milliliters. So yeah, that's for that question here. Let's see what they say. Liter. And exactly. So this here is actually pretty cool in terms of that, how they mentioned it, because the grams can be converted to, if I remember correctly, like mil. Grams and mil are quite similar, and in terms of the cubic meter, so that's meter squared. I believe that's usually compared to kilograms and liters, those three. So here I believe it would be usually meter to meter squared, but no one really talks about that. I focus more on these. These three are usually synonymous because the surface area can be turned to the liters, and the liters can be turned to kilograms as well. Kind of like just that consistency usually, but this in this specific situation is just how much the water level rises through volume displacement. So let's see, and make sure you have indicated markings to actually, you know, figure out how much volume it was. Oops, we don't want that. This is correct. So there we go. All right, so now question 3. How do electron configurations correspond to the periodic table? Me personally, I really like this question because as you can see here, the way the electrons are configured is because, well, not because, they like to go in pairs. So there are 4 types of shells you know about. There are S, P, D, and F. Okay, these are just the shell names, but this also kind of explains in terms of like the specific type of orientation the electron has. So S comes with 1, okay, and I'll explain what each box does. But P has, according to this, just to make sure I remember correctly, 3. 1, 2, 3, 4, 5. Yep. And then D has around, like, you can go up to 2, 3, 4, 5, 6, 7, 8. I believe it has 5. And F, that's the one that goes up to 7, I believe. Okay, and now in each box 2 electrons can fit in. Okay, one electron will be rotating upwards and the other one will be rotating downwards. Just going to draw that a little better. and that applies to every box. I would love to draw it for each one, but it'll get kind of tedious. But that's the idea around it. So pretty much the maximum S can have will be 2, P will be 6, D will be 10, and F will be 14. Now, how does that apply to specifically getting to the periodic table? So the S's, these two, are specifically for the first row, okay? The alkali metals. So hydrogen, lithium, sodium, potassium, and it keeps going on. That is the first row of S. Now you're probably thinking that the second row of S would actually be the next one, the beryllium, but funny enough, it's actually going to be the noble gases, funny enough, because think of it this way. So hydrogen is the first element, okay? So it has, like, you know, the nucleus and 1 electron. That's hydrogen, okay? The way you notate this is 1s1, because this is the first row, and then S because it's the shell, and 1 because that's how many electrons are in there, hence the space it can fill. Now, instead of you skipping down to beryllium, you actually go to the next element. The next element, okay, so this is hydrogen. In fact, I'll make this a different color to keep track. The next element is helium, and that's actually the one that we refer to. In fact, let me just draw it like this. It's an electron, okay, nucleus right there, and 2 electrons on this shell, and this one's actually called 1s2, okay? That is for the S row specifically. Now P is what I kind of call, it's kind of like a giant sandwich, okay? The way I picture it, it kind of goes like, yeah, drawing a sandwich actually. S, and then P, and then D, and then F. The reason why I say it's kind of like a sandwich, specifically for the periodic table, is because the P's actually start at beryllium, so that row right here, okay, if you can see, we'll like beryllium, and it will stop at fluorine, okay? So for example, if you were to write down the electronic configuration notation for fluorine, usually what they do is that to indicate that that row is done, they just put it in brackets. So helium, for example, is finished because you have to go through the whole helium to get to fluorine. And so you skip over hydrogen, you skip over helium. That's what this covers, okay? And it would actually be 1s1, and actually not 1. Whoops, sorry. It would be 2 because now the second row, s1, and 2p5. Now, funny enough, that's actually not what fluorine prefers because it's actually easier and more stable for it. It likes to keep at least one shell. For most things, it likes to keep at least one shell just full if it can. So actually, you can just actually write this as 2p6. That's a more stable form for fluorine. So forego that helium. It's still missing the 2s2 though. So that's what it would do there. Actually, let me just double check here. No, whoops, sorry. Miscounted. It actually is already full. So this would be fluorine. If it was oxygen, that's what would happen there. But I miscounted there, so just to make sure, beryllium is 1, boron is 2, carbon is 3, nitrogen is 4, oxygen is 5, fluorine is 6. So this right here will be the electron configuration for fluorine. That's how you'd write it. What this I'm trying to say is that that is a P row. Now, D, if you're kind of going with the sandwich thinking, if you see here, right, it says all transition metals, right? So that would be where the D shells go. So that's why in terms of configuration, It does get more and more complicated, but the one thing to remember is that for D row specifically, whatever shell you're on, so let's say the shell is N, okay, for D, it's N minus 1. So as an example, let's pick scandium. Actually, let's pick something that we know. Let's pick iron. Might be a little tricky in terms of balancing it out, but the concept is that, so we first start with argon, okay, and it's gonna have the row is 4 now, so 4s1, and it's gonna be 1 2 3 4 5 6, so 3d6. And what actually this prefers is that because this is the lower number, technically the way to write it, you always want to start with the lowest number first. So the proper way would be argon 3d6 4s1. And the reason why it's 3 is because remember for the P rows, for the D rows, you want to subtract by 1. So that's what the D shell refers to there. And now for the last one, the F shells, okay? The F shells, so exactly same concept for F. It's going to be N minus 2, okay? So, and that's all the lanthanum and actinium elements. So let's pick something that, I'm not familiar with any of this, but let's pick uranium, okay? Uranium is a pretty relatively safe bet because we've all heard of that that element, hopefully. So uranium, we kind of just can skip because it's on the 7th row. So radon from the 6th row would do just fine, okay? And we know that it's covered 7, so a 7s1 that's covered. We'll reorganize it later. And the F starts first because it goes straight into it. Uranium is the 3rd one, so it's going to have 1d, because if you remember the actinium and lanthanum series still counts as the transition metal, like in the D row, not the F row yet. So everything after is the F row, okay? So it's 1d, so that's subtract by 1, 6d1, and then 1 2 3, and 1 2 3, that's 5f3. There's probably a much nicer way to write this. 6d1, whoops, 7s1, and that's just an example. In terms of what they actually prefer, that one gets a little bit more complicated, but this would be kind of the concept for this. Now, how does this all tie back together? When I refer to the shells I like to occupy, if you notice, it actually coincides exactly with the amount of rows they are. So S, for example, remember in the sandwich, hydrogen row, helium row, 2 rows only, which is why it's only up to 2. And it's technically just 1, but that's why it's up to 2. Because every electron likes to be paired, usually in terms of like the shell configuration. Now then, P's, because you notice how we have 3 boxes, which means 6 electrons. If you count, beryllium is 1, boron 2, carbon 3, nitrogen 4, oxygen 5, fluorine 6. That's how we got 6. D, 10, okay? And you notice that there's actually 5 of them from scandium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hence why we have 5 boxes here. And if you guessed it, the lanthanum and actinium series, starting after lanthanum, there should be 14 of them. So from cerium to lutetium, it should be 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that is how all of that, in a sense, corresponds to the periodic table. It's quite a long explanation, but this is pretty much the breakdown of it. This picture here specifically shows how the electrons like to fall in line. So if you notice that once you get to the 5s series, so the 5th row of the periodic table, that's the last part, because once you hit the 6th row, you start dealing with the F's, and once you delve into once you deal with, after the 6th row, that's when you start dealing with the F's, and then the 7th row is the last F, but it's kind of how the breakdown of it. And yeah, let me just see what they say about that. Yep, they talk about each alkaline metal ending with S1, and just depending on the row they are, that's how they correspond. Okay, and in group 2 elements, the alkaline earth metals all end in S2. So that one, that part is not correct, because as we discussed, those are more of the halogens that end up in S2, because the alkaline earth metals, that's when they go into the P. So, because they're thinking it more like it's kind of just linear, but think of it more of a sandwich, especially with the periodic table. It's more of a sandwich, okay? Transition metals, exactly, do talk about that. Groups 3 to 12, that one is where we've hit the D shells. And then they talk about the rare earth metals, the lanthanide and actinide series. That's where we hit the F shells, okay? So let's review this actually, just to see. 1s1, 1s1, 2s2. Interesting. Okay, I see what they're saying now. That makes okay. All right. So based on this explanation, if we're going by this is what the textbook says, then in this case, because you know, I want to make sure that the right information is being passed down. So for fluorine, for example, if we were to revise it, it'd be 2s2 2p5. In fact, I'll write it in red so we can keep track. 2p5, okay? And that would be the configuration. Argon would be 4s2 3d. Well, yeah, 4s2. And where is argon here? We agreed that it was right. Nope. Oh, that's what, 'cause I was doing an iron. There we go. So iron, yep, 4s2 3d 1 2 5. Okay, 2 3 4 5. Oh, it's still 3d6 actually. Okay, and then you want to rewrite it, so it'll be 3d6 4s5. That makes more sense. Okay, so this is good that we're able to catch that. So this is indeed correct. So specifically on the periodic table, the only element that counts as a 1s2 but is on the other side will be helium. So if you were to redraw the periodic table to weigh that the helium is not with the rest of noble gases, the table will look kind of like this. So in terms of rough draft, okay, this would be the S series, okay, and then this would be the D series, this would be the P, and then this little bracket here would be the F. So sorry about that, and I'm glad we clarified. So it almost still works as a sandwich, but that only applies for the D and F series. You'll find the F series only in places that have the D series, and you only find the D series between the P and the S. So to emphasize once again, once you hit the alkaline earth metals as they stated, you're still in S2. So to avoid complete confusion, all right, if we pick magnesium, magnesium would simply be neon as a start, okay, and then it'll be 3s2. This right here is magnesium. So apologies for the first statement, okay. And if you want to pick, for example, sulfur, okay, still neon, and then we go 3s2 because it's in the third row, and then you count 1 2, 3, 4, and there'll be 3p4. Okay. So sorry about that, because I want to make sure that this concept is thoroughly understood and we don't want any confusion. So they are correct. So if you made it this far, just make sure that you treat it like a sandwich, but only for the D and F rows. S and P are on opposite ends. The S coincides with the alkali and alkaline earth metals, rows 1 and 2. Okay, and the P coincides with the latter half of the periodic table, pretty much starting at row 13 through 18, excluding helium. Helium is the only one that counts as 1s2. Okay, but everything here as discussed initially, so let me just erase that. Okay, oops, erased too much, but that's okay. But everything discussed initially, in terms of how they like to configure themselves, this is correct. It's just a matter of where on the periodic table, okay? And this is the only example of an S2 being filled, but it's on the 18th row of the periodic table, because although it's a noble gas, it's not going to fill its P shell. That's its S shell being filled. And neon, for example, if you want to write the full thing, you will fill up 1s2. So this is for neon now, okay? And this is the last example. I want to make sure we knock this down. It'll be 1s2 completely filled, and then it'll be 2s2 because lithium and beryllium are filled, and there'll be 2p6. That is neon. Okay. All right. So now that we've really hopefully battered that in, let's go on to the next question, please. Question 4. And now, how do you convert? So more conversion questions. How do you convert 1.1? Whoops, 1 and 1/4. So 1.25 gallons to liters. Now remember, same concept of always want to put what you're converting to in the numerator and what you're converting from in the denominator. So we have 1.25 gallons, which is 1 and 1/4, as I said. So we multiply that by something gallons over liters. So let's see what our conversion table tells us. So in volume, there is 1 gallon is 3.78 liters. So 3.78 on top, and 1 luckily for us at the bottom. So then we multiply those two together. So 1.25 times 3.78, what do we get? 4.725. Just want to make sure that it's a 4. All right, and we cancel out the units, and we get this. All right, and we don't really have to worry about significant additions because they wrote it as 1 and 1/4. So this is what we get, and if we broke it down, we really don't have to, but you can also put it in terms of the same fractions, but I'm sure no one wants to try to figure out what 0.725 is as a fraction. So with that being said, let's see what they did. They say 1 gallon is 4.546 liters will be used for this specific equation. Okay, so that's what they use there, and they do get a different answer, which is why it's important that if your instructor does give you a unit conversion sheet, go by that and don't just go to Google and search it up like I did for earlier questions. Usually when they try to present you with conversion, either it is stated in a textbook or they do give you a conversion sheet, because in chemistry and physics there are a lot of different things to be converting to and from, which is why. So just to double check I use the right one. 1 gallon in this page, 3.78 liters. So yeah, that is correct. Correct based on the factor they used. So the lesson here is that make sure you keep your factors constant. If you're ever not sure, ask a professor, or just go over your notes, because it would be unfair to give you conversion units. I mean, to give you conversion questions without the units. Like even the question we addressed earlier where we had to figure out the distance over time. Because if you don't just know how far, what was it? Was it to June, I believe? I mean, not was it Jupiter? Whatever planet, yeah. If you don't know how far the planet is from Earth, you're kind of already at a disadvantage for that question. And I'm sure nobody just walks around knowing how far every planet is. I know I don't. So, let's see here, another conversion question. Same concept, 1/4 of a cup, so 0.25 cups. And now, multiply over how many tablespoons are in a cup. Go back to our conversion sheet. What does it say? So, tablespoons. Unfortunately, it's not included here in terms of our list. The closest we have is 2 cups is 16 fluid ounces. So for this, we kind of have to make it fair, because I do want to make it a little bit more challenging. We're going to see what we can connect to here and then convert from there. So we have 2 cups here, as you can see, 16 fluid ounces. So let's find out how many fluid ounces in tablespoons. Okay, and the reason, 1 tablespoon is half a fluid ounce. So let's actually do this, because now it involves more steps, but this is just the importance of keeping with your units. So fluid ounces. Remember, you want to make sure that you always keep what you're trying to get to in the numerator. Okay, and we want tablespoon and fluid ounce. Okay, and the reason I wrote it like that is because you kind of just write down what we see there. You can technically write 1 at the bottom and 2 at the top, but I'm just keeping track of what was given. So let's just exit out of there because we didn't really have a choice. Now let's go back to this. 2 cups, 16 fluid ounces. So 2 down here, 16 over here. And now let's see if we kept track of our units. Yep. And yep. Okay. So now let's do the math real fast. So it'll be 0.25 divided by 2 times 16. So it really is times 8 and then times 2. So in total it'll be times 16. So 4 tablespoons should be the answer, but it's always good to double check with a calculator. Okay. So 0.25 times 16 divided by 2 divided by 0.5. Yep, the answer should be this, based on our units specifically. And let's see what they get. So they just went straight to it, where 16 tablespoons are in a cup. This is just in case if you ever see tables like this, sometimes they give you pieces here and there, which is why I broke down this question like that. The important thing is just keep track of your units and you should get to the right answer, okay? And so this is correct. Alright, next question. Question 6, I believe. Yep. How to convert acres to square feet. Wow, a lot of conversion questions tonight. So, with that, acres to square feet. So, they want acres and they want to get to square feet. So, you're given acres. So, same concept here. Okay? Put what you have in the denominator, acres, and what you want in the numerator, square feet. That is the way. Like right here, this is the whole question. In fact, I'm gonna write down a note if you want to take a picture of this. So numerator has unit you want, and denominator has unit you have. This is the golden rule for most, if not all, chemistry questions, to keep track of your units and make sure you're converting the right way and not multiplying things when you should be dividing, okay? So let's look at this. What are we dealing with? Do they even have the acres? According to this, no, they do not. So this actually is perfect. Whatever they give you, that's what you put in. So whatever your conversion factor says, just make sure you put it in the right spot. If they say 1 square foot is equal to 3 acres, for example, you put 1 here and 3 here. That is what you do. And in a sense, you're just dividing this by 3 to get your answer. If they say 0.7 of a square foot is 2.2 of acres, same concept. You multiply it by 0.7 divided by 2.2 and you get your answers, because these units will cancel each other out, give you just a square feet, which is what you want in terms of this question. Let's see what they say. So, wow, I was way off in terms of my examples. Turns out 1 acre is quite a lot of square feet, but this right here, if I can actually highlight it, no, I cannot. If you can see my pen hover over it, this right here, this is a golden thing. You see how they have square foot in the numerator and acre in the denominator? This is how you're going to do that, okay? So with that, this is correct. And now we're going to move on to question 7. How many? Wow. Another conversion question. Well, let's try this again. How many pints are in a quart? So remember, the way they phrase this question, right now you have quarts, because it's asking you how many pints are in. They want to get to pints, but they're giving quarts. So again, you write down your quarts in front and you multiply by what you want, pints, over what you have, quarts. So let's look at that nice golden rule right there. And this is really what you have to do. So hopefully this time we actually have values, because it'll be a lot easier to explain with actual numbers. So 1 pint, oh nice, this actually is a perfect example. 1 pint only goes to ounces, okay, and then quart also has ounces there too. So you kind of have to do a multi-step thing. But you see here, right, in terms of volume, the only thing connecting the quart, dang, they have it right there. 1 quart equals 2 pints. That's a shame. But let's assume that it did not tell us that. Let's assume that this right here wasn't there. Let's do an extra step with fluid ounces. So same concept. You start with quarts, and now you see you have to get to fluid ounces, because that's the only thing connecting pints and quarts. So the full thing would actually look like this. Okay, quarts still in the denominator, and you want at first fluid ounces. So according to this, 32, and this will be 1. And now you have fluid ounces, same concept, you want to get rid of it to get to pints. Okay, and that would be 16 according to this sheet, 1. So funny enough, all this together, you really do get the same thing as they say, 2 pints per 1 quart. So that is conceptually how this works, so keeping up with your digits. I was hoping that it didn't just give us the answer, but this is the concept here that you'd follow. So just as they say, in your standard volume, there are 2 pints in 1 quart, and exactly, always be referring, very important, to your sheet that they've given you, your conversion sheet. I can't imagine doing chemistry without a conversion sheet, just because especially when you stray away from just like solving equations and go more towards trying to figure out like how many grams or something you have, and when you're given like, I don't know, like exactly like in terms of volume displacement question, like, oh, this amount of volume was displaced, and then you have to figure out how many grams you have. A conversion sheet is always good to have. Okay, so now let's move on to question 8. Okay, how do you convert 30 centimeters to inches? Well, hopefully we've kind of gotten a grasp of this, but same concept. You have 30 centimeters and you want to go to inches. Alright, so that is how that would work. Make sure these units cross out. So centimeters in the denominator. And now let's see in terms of length and distance. 1 inch is 2.54 centimeters. 2.54. Okay. Units, as you can see, will cross out when we try to solve this question. Okay, let's get onto our calculator. 30 divided by 2.54, and really 11.8, or if we round it based on the significant digits, we get 12 inches as our answer. Okay, and that would be how you convert it. So once again, as you can see, they keep their inches at the numerator, that's what we want, and centimeters at the denominator, that's what we have. Cancel out, they also get that 11.8. So this is correct. And let's move on. So now with that, let's move on to question 9. Another conversion. I hope, actually, you know what, this is fine. It's really going to help everyone watching nail the whole conversion sheet. I wish there was a way to interact, because I'll probably ask you which one we put in the numerator and denominator. So how to convert quarts to gallons. So this time, okay, we start with quarts and we want gallon. And now you can kind of start seeing how your conversion sheet becomes your best friend. If you're ever in doubt, well, even what I like to do is when I'm kind of lost in the question, I go over in the conversion sheet to give me hints in terms of the information presented to me in that question. Okay. If your professor or teacher says memorize the basic conversions, I go ahead and start memorizing it because then you know that they're gonna play a role in whether you have quizzes or exams and such. So here we have it. 1 gallon is 4 quarts, so 1 4. So whatever you have as the initial starting quarts, it'll be 1/4 of it. If you start with 1 quart, it'd be, let me just write down possible answers. If you start with 1 quart, you get 0.25 gallons. If you started with 4 quarts, you get 1 gallon. Start with 6, you get 1.5, etc. Just make sure you plug into the calculator to get your answer. But exactly, units still cancel out to get gallon. So with that, this is also correct because they also have the gallon in the numerator and quart in the denominator. Alright, now let's see what we have as our last wrapping question for tonight. What is the mass of an electron in atomic mass units? Now, funny enough, this is also a conversion question. Ta-da. So, question 10, we are converting mass of electron, okay, and we want in AMU. So the mass of electrons usually comes in kilograms as reference. This is typically, and the we want atomic mass units as the top. Okay, so with that, you're probably wondering 2 things. What is the mass of an electron? And what is an atomic mass unit, aka AMU? So let's take a deep dive in both. Mass of electron, simply put, I have been taken a lot of chemistry courses, and knowing that by heart was not one of my required knowledge. I believe it only became truly required when dealing with physics and all the complications there. So hopefully they also don't require that of you, and they've given you a second type of conversion sheet, or more specifically, they're giving you it's kind of called a constant sheet, where they give you common constants and values that you typically use in chemistry or physics. Here we actually even have atomic mass unit as well. Mass of an electron. Well, that's not fun. They gave us the answer as well. Let's say they only gave us the grams. Okay, so like I said, it's usually in kilograms, but in this case it's in grams. Okay, and we have to now adjust and still try to solve the question. So the mass of an electron, okay, according to this, is 9.109383 times 10 to a negative 28 grams. All right, so that's the mass of an electron. Now, what is an atomic mass unit? What does this mean? So now, funny enough, right? You know how people always refer to, well, carbon. So if you actually look at the periodic table, when you try to get, in a sense, the value of how do I put this, 1 unit of an element, you were probably thinking like, oh, hydrogen would probably be the best bet because it has 1 proton, 1 neutron, 1 electron. But as research has shown, carbon is actually considered one of the most, how do I put this, perfect elements, just like referring things specifically in terms of mass. Really, a lot of the periodic table is actually based on, if I remember correctly, it would either be carbon or, yeah, I believe it's carbon. But the point being is that the atomic mass unit specifically, funny enough, is instead of just saying how much a hydrogen weighs, I'm pretty sure because that would also be a lot hard to do, they decided to figure out, based on, you know, the the molecular formula and the molecular weight of carbon, right? They divided that by 12 in terms of the mass of it. For 1 carbon, they divided by 12 to be able to get that number. So the atomic mass unit, if you see here, this 1.660539, this is actually referring to 1/12 of a carbon molecule. So that's just a fun fact, but point being is that we do need it. 0.5390. Ooh, that's a big number. Let me stop the 9. Let's make it 91 times 10 to a negative 24 grams. And the reason I say this is a conversion question is because they show right here 1 unit. Okay, so 1 unit is this many grams. And there. So now we have the mass of an electron. Oh wow, I really like this feature actually. And we just plug it in, because you notice these two cancel out, and once you make these two numbers, in a sense, fight, I guess, because they're quite tiny numbers, to negative 28 and negative 24, make sure you put into your calculator the right way. 1093. Oops, let me make sure. 9.109383 divided by 1.660539. Oh, divided by 60. Okay. 10 to the negative 28 minus 10 to the negative 24. So that'd be left over 4, but pretty much the answer you get is 5. Actually write it in red so it's distinguishable. 5.48 6 around there times 10 to the negative 4 atomic mass units for 1 electron. That is how much it takes up. So funny enough, when you actually now go over to the mass of the electron, what do we get? 5.486. Funny enough, that is the answer right there. So they actually already gave us there, but just in case it doesn't give you the atomic mass units and just gives you the mass in terms of grams, and they give you then a separate section with the AMU, that's the conversion you take. So this is another conversion question in a sense. So with that, just double checking we have everything. How they solve it? Yep, 5.48 rounded 6 to 4th decimal place over. So that's 10 to the negative 4. This is correct. Now, before I submit this question, I do want to go back because a lot of these questions were just conversion and then one doohickey giant question about S, P, D, and F. This is the one I want to review because specifically these questions do come up in terms of electron configuration. I would say once you get to that unit, it does come up quite frequently in terms of trying to establish what that element is configured as. So the important thing is, as they did say in this nice picture here, just to mark it as different sections, the S is the first 2 rows of the periodic table, okay? The alkali and alkaline earth metals, all right? And the only exception to that, as in the only addition to that, is helium. Helium is 2s2, not 1s2, 1p1. I mean, not 1s. Whoops, sorry. Helium is 1s2 because it's the first row, as you can see here. Helium right there. Okay. So helium you'd write as 1s2. It is not 1s1, 1p1. Okay, just because it's on that side. That's why I kind of just throw it in there. So this is not correct. Now, moving on to the P, starting at, as I said, row 13, boron, over to neon. So we do not include helium. That is the P. Okay? These are the P elements. All right? So, with that, neon, as I said, the way you'd write that, let me see if I wrote it. I did write it. There we go. Neon nope, that's for fluorine. No, I wrote it down somewhere. Well, let's just write it down again. So this one here is an example of helium. It's just 1s2. Neon, okay, if you want to write down the full thing, you have to include the 1s2, but you just start a helium and then you go over the now second row, so that's 2s2 because it includes the 2 lithium and beryllium, so the first 2 elements of those rows, the alkali and alkaline earth metals, okay, and then 2p6. This right here would be neon, okay, and fluorine, and that's the one I had up there, but pretty much if we had fluorine, okay, it would still be the helium, okay, and the first 2 rows would be filled indeed, and it would be 2p5, and if I remember correctly, there are ways to distinguish in terms of like which ones they would prefer to have full, but that's not what we're going into. We're just kind of explaining how each electron configuration matches in terms of like the rows. So as I said, this is 13 through 18, and I'm put asterisk here as to say not included helium, okay, because helium is over here, helium is here. All right, and now D, the D shells, D rows, okay, they're these ones right here. Okay, so these ones are known as the transition metals typically. So from 3 to 12. Okay, 1 and 2, 3 to 12, 13 through 18. Okay, 3 to 12. And as an example, if you want to run that one back, let's say you want to iron again. Okay, so iron, this right here is what it would look like, and then the more correct method would be to organize it by, remember, because D is -1 and -1 as we discussed, because it's now whatever row you're on, you subtract 1. So we started at argon 4s2 because potassium and calcium are filled. Okay, why do I have a 5 there? 4s2. Okay, and 3d because we're starting at the 4th row, but it's D, so -1, 2, 3, 4, 5, 6. So 3d6, and that would be for iron. Okay, so this right here would be how you write iron. And now for the last one, the lanthanum and actinium series, they're right here, and this is where all the F shells go. Okay, and I'm really emphasizing this because I don't want anyone to be confused as how I explained it earlier. That would be an error on my part, which is why we're back on this question, and because we have a little bit extra time just going over it. So once again, like I said, that's the F series, and now we're dealing with -2. So whatever row you're on, you subtract 2. So if you want to pick uranium again, so let's do that fun one again. So that'll be Rn starting, okay, and then it will be 7s2, not 7s1. Okay, Rn 7s2, and then we have 6d1 because you still have to start at actinium, and then you have 1, 2, 3, 5 F3. So that would be the actual correct one. So, and there's probably more ways to do in terms of like how they prefer their shells to be filled, but it would go 5 because we want to make sure it's in order. 6d1, 7s2, and the reason why, because that is where the confusion for me began. Because if you notice, the only shell really that gets interrupted, like when you want to count normally on the periodic table, the only shell, as you notice here, that gets interrupted mid counting is the D shell row. Once you hit the lanthanoids and actinoids, those ones, they have a D1, but then everything after that starts being F before they get out of those series back to the transition metals. So the way it's shown here is a little bit, oh, look at that, not what I meant to do at all, but let me refresh that. So the concept is that the lanthanum and actinium, those two count pretty much as transition metals, as that's what they classify as, and then there's like a little sliver after it, and that's where they have literally every of the lanthanum and actinium series. That's how the interruption happens, hence how we have the 1 followed by the F's that come up. And with that, that is all I have for tonight. Hopefully going over this question again has cleared up some confusion in terms of how to count it. Just remember that other than helium, the S's are the first 2 rows, the P's are the last 6 rows, the D shells are in between, so 3 to 12, sorry, and then the F is just the lanthanum and actinium series, not including lanthanum and actinium themselves, because those ones are still technically in the D shell row. Okay, some periodic tables will show that better, because they'll show like if I drew that section in the middle, they would have the LA and AC, and then right here, this is where they branch off. So kind of look like that, and then this is where they branch off to the rest of the series. Hence why LA and AC are still there. But yeah, thanks for staying with me through this whole tutoring session. I just want to thank you again. With that, hope you have a wonderful rest of the evening. Happy holidays once again, and have a good night. Okay.